So we are very pleased to have today Kevin Zahnle. And Kevin, I think was it your PhD thesis work, or was it an outcome of your PhD thesis?
It was in the thesis, and then about 3 years later, 4 years later, I published it.
Yeah, so it was
It
just
was
about
already old.
of
Yeah,
your
it was-
thesis. So
Yeah.
he published with Walker, who was your advisor, I think.
Yeah, Jim was the advisor. And, well, I don't want to, I better stop talking. I'm
A
just not.
very provoking idea that in the past, in the Precambrian, the atmospheric tidal torque counteract the normal tides, the body tides, and this result in a locking of the rotation of the Earth for a very long period of 1 billion years and even more. And this idea was left for several years, but recently there was some revival first in a first paper, and very recently in this summer there was 2 papers that came back to this scenario, and one in Nature Geoscience, the other one in Science Advance, reviving this scenario. And so, as we have published papers that are quite in an opposite way, it's very nice to see what are the present thoughts of Kevin about this problem. And this is why I asked him to go back to his 40 years ago.
To my childhood.
Yeah, to your childhood, and to present us your thought and your feeling about this controversial issue.
Thank you, John.
Now you can share your screen, and you are welcome to start.
Are you ready?
Yes, we are.
Are you all sitting comfortably? Well, then let us begin. I came up with a new title now, The Years the Day Stood Still. It harkens to some famous science fiction movies. This all feels like science fiction to me. So it's back. The resonance hypothesis and the evolution of the semi-diurnal atmospheric thermal tide on Earth. And I show a screenshot of one of the papers where it came back. And if you'll look at this screenshot, you'll see the length of day is the y-axis, and the x-axis is the age in the history of the Earth. Today is on the right, and the beginning of time is somewhere over under the letter E for Earth. And what are known data or published data for the length of day? It's been interpreted. There's actually nobody actually was counting the number of days per year or the number of hours per day in the Proterozoic. But this is known as the boring billion period, from about, it's usually run from about 800 or 900 million years back to about 1.8 billion years. The reason it's called the boring billion is that not a lot happened on Earth that shows up in the geological record. Metazoa had originated before the boring billion. The boring billion has oxygen in the atmosphere, but not much. It has an ozone shield. And no glaciations. So it's relatively warm period in Earth history. And the question is whether you should be drawing a red line through these data. So you may ask, what is an atmospheric tide? Be patient, we'll get to that. First, we need to speak of ordinary tides. Ordinary tides are the friction between the movements of the celestial spheres. It's essential to celestial mechanics to have friction, and this is the friction. An ordinary tide, you're familiar with the gravitational tides. Here we have the Earth and Moon. There are 2 high tides each day. The explanation dates to Newton. And we call it semi-diurnal because there are 2 per day. The lunar gravity is relatively stronger when you're closer to the moon and relatively weaker when you're further from the moon. compared to the centrifugal force that balances the gravity at the center of the Earth. And so the atmosphere, ocean, and solid body are pulled elongated towards the moon. There are a vast number of other gravitational tides driven at other frequencies, but the semi-diurnal is the most important in most places. But it's dissipative, and there's a finite response time that causes the tidal bulge to get in front of the moon. And so the tidal bulge is pulling on the moon, and the moon is pulling on the tidal bulge. So the tidal bulge is trying to speed up the moon, which lifts the moon's orbit, and the moon is trying to torque the Earth in the direction opposite of its rotation to slow us down. In this particular tide, the angular momentum of the Earth-Moon system is conserved. The sun also raises gravitational tides. Very similar story. The finite response time causes the tide to get in front of the sun, and the sun pulls on the tidal bulge to try to slow the Earth's rotation down. This one decreases the angular momentum of the Earth-Moon system and puts that angular momentum into the Earth's orbit around the sun. There are tides in the atmosphere. There are gravitational atmospheric. Hi. There are gravitational atmospheric tides raised by the sun and the moon, but the more important tides in the atmosphere are thermal, and they're raised by solar heating. Oddly enough, the most important atmospheric tide on Earth is observed to be semi-diurnal. And you may ask, why? What is this about semi-diurnal solar heating? The sun rises and sets once per day. That's diurnal. But the shape of the heating is something like a sombrero. You don't have any solar heating at night at all. Then when the sun rises, the heating increases to noon, then it drops back down again. This is when the sun sets, and there's no heating at night. So you do a Fourier transform of this thing, and you see that you have a big diurnal term, but the semi-diurnal term is quite large, and it's something like 15% as big as the diurnal term. So there's a lot of energy actually in semi-diurnal forcing. When you measure the atmosphere, you see these tides. The phenomenon was known to Kelvin. I'm getting a lot of crap in my screen that I have to try to look through. The tide is obvious in the tropics, and you'll see this little ups and downs here in Jakarta twice a day. It's not obvious at all in the polar regions like Germany or France. You can barely see it because the Rossby waves are so much bigger, and fundamentally the semi-diurnal atmospheric tide is a tropical phenomenon. So Sir William Thomson in 1882 wrote, he actually gave a lecture in 1881 and then wrote it up in 1882, titled On the Thermodynamic Acceleration of Earth's Rotation. Sir William Thomson used the available barometric data, and he saw that the semi-diurnal tide was bigger, much bigger than the diurnal tide. So he wrote that the semi-diurnal tide must be nearly resonant with a natural period of the atmosphere. He was right. He wrote that the negligible amplitude of the lunar tide means that the atmospheric tide is caused by solar heating, not gravity. He was right. Also known as Lord Kelvin, but he wasn't known as Lord Kelvin. He was a mere Sir William Thomson. It was said, I think it's said in Wikipedia, someplace like that he has more letters after his name than any other person in British history. The solar semi-diurnal atmospheric tide is caused by solar heating. So in this tide is a forced wave that follows the sun. So as the Earth rotates, the wave is fixed with respect to the sun. Today, it concentrates mass at 10 o'clock and 22 hours, while the peak temperature is at 4 and 16. If it were a purely linear, if it were just the atmospheric being heated, it would be at 9 and 9 and 21 and 3 and 15, there is a lag that is generally thought to be due to the ground providing some semi-diurnal heating of the atmosphere as thermal infrared. And that changes the phase slightly. The torques on this tide are on the pressure amplitude, on the pressure bulge, and the torques are in the same direction as Earth rotation. They would speed up Earth's rotation. So solar gravity tugs on the bulge, and it's trying to speed up Earth's rotation. This increases the angular momentum of the Earth-Moon system, taking the angular momentum out of the gigantic reservoir of Earth's orbit. Because the energy comes from sunlight, the torque does not depend on dissipation. It is more like an engine getting its energy out of solar heating. So Thomson went a little further, and he compared the thermodynamic acceleration to the total rotational deceleration that Ames is one of the mathematicians or celestial mechanics who predicted the position of Neptune in the sky. He was the one whose prediction was ignored, and so he didn't get credit at the time. But he became the astronomer royal later. So he worked out the history of total rotational deceleration of the Earth from historic eclipses. Kelvin estimated that the thermodynamic acceleration of Earth's rotation was only 10% as large as the deceleration. He seemed a bit disappointed that it wasn't larger, so I found the only image of Kelvin I could find that shows him looking disappointed. A modern estimate using more complete data is closer to 6% than 10%. But it's not zero, and something has to be accounted for, I would think, because you want to have the angular momentum of the Earth-Moon system as a known quantity. But wait, your title said something about a resonance hypothesis. Could you explain that? I'm glad you asked. Kelvin's hypothesis that the semi-diurnal tide must be nearly resonant was discussed, nearly resonant with the natural oscillations of the atmosphere, was discussed for 80 years. A 24-hour resonance went in and out of favor several times. The story is told blow by Chapman and Lindzen in 1970. It's a good read because they don't reveal the answer. They keep going along step by step and keep you on the edge of your chair to the extent that a scientific paper can keep you on the edge of your chair. Along the way, a fellow named Holmberg made the total awesome suggestion that why don't the 24-hour day is actually fixed as a balance between the resonant thermodynamic acceleration and ordinary tidal dissipation. This is despite all the numbers that would tell you that that couldn't be. In any case, the problem was solved in the 1960s. The semi-diurnal tide is big because sunlight is absorbed by ozone. So the earlier attempts to use the resonance to enhance the semi-diurnal tide was to use an insufficient source of energy and then make the tide bigger by having it at resonance. It turns out they've been neglecting ozone absorption of sunlight, and that's actually a significant amount of energy absorbed by ozone, and that drives the semi-diurnal tide. The resonance for Earth today would be at 10.65 hours. That was kind of understood, certainly by 1960, and not at 12.0 hours. So the resonance is actually not at the current Earth rotation rate. With a different atmospheric structure, with a major, if you had a much hotter stratosphere, you could get a second resonance in the atmosphere, but most atmospheres only have one such resonance. But because it's at 10.6 hours, which would be a 21.3 hour day, it happened in the past, some 600 million years ago. So that's what we suggested in the 80s. If the resonance is at 21.3 hours, it had already happened. It happened 600 million years ago. And so then we supposed that there was a torque balance in the late Precambrian. We found that to get a torque balance, we needed minimal dissipation in the semi-diurnal tide, we needed Q's greater than 100. The dashed line here is for Q greater than 100. And of Q of 100. And I think this might be 200 and this might be infinite because, well, you know, nobody's going to read the paper. Oceanic tidal torques are being labeled here. The current oceanic tidal torque is not this big. It's actually more like 6. I'm not quite sure where I got this big number from. This might be, this is probably extrapolated back into the past from the current, actually. The Phanerozoic is the average during the Phanerozoic obtained through various proxies. People count things like growth rings on bivalves and so forth. The Precambrian rate, though, of tidal dissipation had to be more like 2 times 10 to the 23 9 centimeter, or 2 times 10 to the 16 in Newton meters, to use SI. Because if you were to take the current tidal dissipation and then evolve the moon back in time, you find that the moon and Earth are about 4 feet apart 1.5 billion years ago. Then that's just not an acceptable answer because we know that they've been a pair for 4.4 billion years. And the explanation with your oceanic tides is that they're also subject to resonances. The oceans were further from resonance in the past, and they are approaching resonance in the future. So we suggested that the day might have been 21 hours for a long time. On this one, on this figure here, you'll see that we have the tidal torque that accelerates being bigger than the tidal torque that decelerates. So we can get a balance at these points in this region of a 21.1 hour day. You'll also notice that on the other side of resonance, the thermodynamic acceleration is no longer an acceleration, it's a deceleration. And now the atmospheric tides have joined the other side earlier than resonance. So perhaps a 21-hour day lasted for a long time. And so we made a little plot of that. If you keep constant angular momentum, which ignores the thermal tide, you get the solid line. But maybe the day length was fixed. And we fixed it here at 21 hours and we drew a dashed line. As you'll notice, this is barely a computer model. It's more like something you do with a ruler and a straight edge. You'll note that these authors extrapolated to the beginning of time, again, because no one will ever read this, so why not? And this is a screenshot from the original paper, and not a lot of data here to work with, really. Not much at all. So nobody paid attention to it except David Stevenson, who did read the paper and thought about it for a while, 29 years or so, and then he gave it to a student at Caltech, somebody that can do math better than I can. And they did a canal wave theory of tides. And this is a screenshot from their canal wave theory. And they simply were comparing torques to a modern and a Precambrian lunar tide torque. And they get really kind of big torques for the atmospheric tide. I'm not quite sure why they're so big. They do use rather large Qs. Although Q of 50 is going to turn out to be not all that bad, and that would be this one here. But in their model, there's plenty of tidal acceleration from the thermal tide. You'll note that they've moved into SI units here. But these are still pretty, these are not terrible. This is not a terrible value. I just think that their torques seem a bit on the high side. I'm not quite sure why. They then did a little model that involved escaping the resonance, which I won't discuss, how you'd escape the resonance, because we're discussing whether it actually existed first. There's no point in worrying about escaping it if it didn't ever happen as a locked length of day. So this is their locked length of day model, and these are their data. They don't really put error bars out here because they're aware that the error bars are as fictional as the data at this point. And you can't put a lot of weight on these data. But there's their toy model. And so the length of day in their toy model increased until it locked in and the resonance sat at 21 hours for 1 billion years or so, and then escaped the resonance and then continued on its slowing down. A couple words about ocean tides. I said that they were further from resonances in the past and they were weaker. This is a full featured ocean tidal dissipation model from Daher et al. 2021. They're also interested in the tidal locking, and I don't know if their paper has been written yet or been submitted. Today, the current tidal dissipation rate is over here in the corner at about 6 in 10 to the 16. Now notice that we're using another unit here. This is also an SI unit. This would be Newton meters, but they don't write it that way. And then their best model, their nominal model, is this black curve. And they did a whole bunch of Monte Carlo things. You know, all these little gray things are different Monte Carlo realizations of possible histories of the Earth. And what they find is that most of their tidal dissipation models, and I think they forced the model to last 4.5 billion years because it's not really acceptable to have the moon hit the Earth somewhere later than that. So I think they use that as a forcing point. The average tidal dissipation, particularly in the Proterozoic, the boring billion, is about 1/3 of what it is now in most of their models. So bear that in mind, that that 6% is actually going to be more like 20%. The semi-diurnal tide, if we do nothing, the semi-diurnal tide is 20% as large as the lunar dissipation. So it's already a big term. That's already no longer you can't neglect it if you're doing a history of the lunar orbit. Yeah, I'm complaining here about the SI units not being consistent either. Very confusing for those of us who like centimeters and grams. Anyway, the mid-Proterozoic units are sort of around in here. Your best fit is about 1/3 of what it is today. So at this point, you're getting confused, right? What is this resonance? Did I ever say what it was? It's a resonance between the solar semi-diurnal forcing and the westward propagating K=2 atmospheric gravity wave. So this is a gravity wave that has 2 humps as it goes around the Earth. It is not fixed. Unless it's at resonance, it's not fixed to the solar forcing, but it's a little bit faster or a little bit slower. At resonance, the wave is coincident with the forcing and it is resonant. Farhead et al., or maybe Lascar et al., I'm not sure which of these 2 papers first suggested calling it the Lamb resonance. It's a good name for it. Sir Horace Lamb did poke a lot at the resonance theory of tides in circa 1910. Like most people that are interested in this, in global atmospheric waves, they would poke at this. There are 3 ways to compute the frequency of the Lamb resonance that work, 2 of which work. LaPlace's tidal theory for force modes can be used. This is the most direct approach, and it's the one that we understood in 1987, where you know the forcing frequency, and then you find, well, Laplace's tidal theory is a linear theory, and you can find the eigenvalues for the force modes. Or you could, number 2, a different way to do this is you could use Laplace's linear tidal theory to find the free oscillations or the normal modes of the atmosphere. Now, this allows you to compare with the current atmosphere to see how well the Laplace's theory is doing, and will show that the current atmosphere, it behaves extremely well. The Laplace's theory does very well with the current atmosphere, and it tends to verify the linear approximations made by Laplace. Or a third choice, you could try to run a GCM at different rotation rates and hope for the best. This is the only practical approach to nonlinear behavior, such as resonance-induced weather. So, number one, we're going to use Laplace's linearized tidal theory for force modes. The eigenvalue of the sun-synchronized semi-diurnal wave corresponds to an equivalent depth. What's equivalent depth? Equivalent depth is the depth of a globally uniform ocean with the same response. So Laplace developed his equations and for an ocean of uniform depth. And then he said, well, you know, this applies to the atmosphere probably better than it does to an ocean because the ocean's got continents breaking them up, but the atmosphere is pretty uniform. And so I want to use the same theory. So I want to have an equivalent depth to describe the atmosphere. And the atmosphere has such a thing. The equivalent depth of the sun-synchronized semi-diurnal wave, that's the forced one, is 7.852 kilometers. The actual equivalent depth of the atmosphere is determined, you can determine it by numerical solutions of atmospheric structure, or what Sakazaki and Hamilton do is you get it empirically from the normal modes of the atmosphere. And the best fit is 10 kilometers. So the correspondent resonant length of day is 24 times the square root of this ratio, 21.3 hours. So that's what you'd expect to find. So I'm standing with what we said in 1987, 21.3 hours is what the current atmosphere would resonate at. You can also use Laplace's tidal theory, as I said, to define the normal modes. The eigenvalues of the free modes will then be determined by fixing the equivalent depth of the atmosphere to the known value of 10 kilometers and then varying the planet's rotation rate. And this is what Longuet-Higgins did in 1968, a paper it took him 5 years to write. And if you've ever seen the paper, you can see why it took 5 years to write. Sakazaki and Hamilton show that the linear theory works well, and I'm going to show this in the next couple of slides. What they've done is they have retrieved the free and forced oscillations of Earth's atmosphere today from 37 years of global weather prediction models. So this is basically a sophisticated way of interpolating real data. So the global weather prediction models assimilate real data, and then they fill in all the gaps. And so that's where your information is. And so you get that, you go and you analyze those weather prediction models. On the y-axis, we have frequencies and cycles per day. So 2 cycles per day. There's your semi-diurnal right there. And these will be zonal wave numbers. The negative wave numbers correspond to westward propagating waves, and the positive wave numbers to eastward propagating waves, and 0 is a standing wave fixed to the topography of Earth. There are symmetric waves, which are symmetric with respect to the equator. There are antisymmetric waves, which are antisymmetric with respect to the equator. And as you can see, they're all there. Look at them all. I find this an absolutely spectacular image because they've found all of these waves, and they all have, we can identify them all. These purple dots are all gravity waves. These are all just families of gravity waves of 1, gravity waves 2, 3, etc., etc. There are Kelvin waves. These are eastward propagating canal waves. They're the naive thing you would do. This wave here, well, I'll get to that in a moment. There's Rossby waves as well, and these are westward propagating. These are I don't know much about Rossby waves. I do know, though, that the theory starts having issues because the frequencies are slow enough that the mean flow of the atmosphere kind of defeats some of Laplace's assumptions. We'll focus in on the ones that are the waves that are of most interest to us. We're most interested in these 3 waves here, the lowest gravity waves. You will have marked here S2 refers to the solar semi-diurnal forced wave. And you can see that the solar semi-diurnal forced wave can occur westward propagating, eastward propagating, anything. they can be shot off in all directions because solar heating is not uniform, and you can get waves going in both senses, but there it's recovered. The lunar forcing is much simpler, and so you see a simpler normal modes, force modes associated with it. Diurnal forcing, there it is. You do expect it. These guys are the Kelvin waves. This 33-hour wave is the naive wave you get if you say, how long does it take a sound wave to go around the Earth? Go around the circumference of the Earth, and that gets you 33 hours. This is the toy model that Wu et al. Used, and the toy model that Bartlett and Stevenson used was a canal wave model. So they were basically treating these waves as kind of Kelvin waves. This would be a semi-diurnal Kelvin wave. I guess that's, well, a 2 anyway. Now you'll notice how close the solar forcing is to the natural frequencies of these three gravity waves. This one, with wave number -2, is the westward traveling wave. So when this wave, well, we're interested in that one. This is the one we're interested in because this is the one that, when it's resonant, will put the solar forcing on a normal mode. So continue on this. The periods of the free modes are shorter for shorter days. This is something that Wu et al. Did not understand. That when they ran their GCM, they got a 22.8 hour resonance. And they said, ha, it's a perfect fit, but they're wrong. The periods of the free modes are shorter for shorter days. They're a function of the rotation rate of Earth. So if you actually do this approach correctly, you will find that the period of the westward traveling semi-diurnal free mode coincides with the resonance when the length of day is 21.3 hours. And so the two approaches using LaPlace's theory get the same result. You could run GCM, the different rotation rates, and hope for the best. And I'm suggesting that it doesn't work that well, although I do not know why. Their two GCMs found resonant periods of 11.4 and 11.5 hours, 22.8 or 23-hour days. This period is in good agreement, they said, with the resonance period measured by Sakazaki and Nakazawa. What Sakazaki and Hamilton found was that the free mode today is at 11.4 hours. So they thought that this was verifying the GCM, but this is not true, because the period of the free mode changes as you change the rotation rate of the Earth. The free mode would not be, when the length of day is 22.8 hours, the period of the unforced wave would be 11.0 hours. It would not be 11.4. So, because frequencies of normal modes depend on rotation rate. It seems that GCMs have trouble pinpointing this resonance. It's probably not a surprise, because these waves are the depth of the atmosphere. They basically extend from the surface to the stars. And so the upper boundary condition becomes a major issue in a numerical computation of these frequencies. And that's something that the analytic models can actually do better, because they just run things to infinity. So what's new with the resonance hypothesis? Well, there's a bunch of papers that just appeared. Mid-Proterozoic day length stalled by tidal resonance, Mitchell and Kirshner. The balanced billion, Mitchell and Evans. Why the day is 24 hours long. The history of Earth's atmospheric thermal tide. That's Wu et al. In Science Advances. Hooray! Did it really happen? I'll be famous. Getting pretty excited. People started phoning me from graduate school. Hey, I heard that what I heard over beer one day. It's in the news. We don't think so. And that's you guys. I only have the archive preprints for your papers, so I can't give you the full citation. We'll get to this. This we don't think so stuff. This is the Wu et al. Idea. They built a model it's pretty well described in Laskar's paper, where they fit to the data. They fit their model to the data. According to the editorial correspondence, it took them several months to do these fits. So there are these machine learning things or something like that. The data are pretty bad, but it didn't stop them. And in order to get this history of the length of day, it got down to 19 hours, and then, well, it's kind of funny shaped, actually, that it got long, and it got short again, and then it got long again. They have an amplification factor that they treat as a free parameter, that they amplify tidal dissipation, and to make the torque big enough to get a balance. So the atmospheric torque is made big enough to balance the ordinary lunar tide, is something of a ansatz. I have no idea what time it is, by the way, so I'm just going to keep babbling unless you tell me what time it is.
You have still 20 minutes.
Okay. The length of day in this model is something like 20 hours during the resonance, but it gets quite short. Mitchell and Kirshner are simpler. They draw a red line here, and there it is. It looks like it's an eyeball fit. They don't have an actual model to do this. They just say it looks like it's kind of flat in there. So it's good to know that this is now in the news, but it's a very short day length. It's something around 19 hours. And why is that important? It's because you want to know what determines the period of this Lamb resonance, and it depends on the equivalent depth of the atmosphere. So to get 19 hours, you need to have a very hot atmosphere. Now, in general, equivalent depth is a property of the vertical structure of the atmosphere, and you would do it with numerics. You would find it with numerics. But there are two easy analytic solutions. One, you can have an isothermal atmosphere, and then the equivalent depth is gamma, the ratio of specific heats, times the scale height of the atmosphere. So the scale height is proportional to temperature and inversely proportional to mean molecular weight. For a dry adiabatic atmosphere, or what Lascar calls a convective atmosphere, the equivalent depth is actually equal to the scale height at the surface. So the scale height of the atmosphere depends on the tropical temperature. I emphasize this is a tropical wave, and so you're interested in the tropical temperature. You're not interested in the temperate zones. And it depends on the mean molecular weight. So if you want to get a much warmer atmosphere than today, you need a much bigger scale height than today. You need a hotter atmosphere or a lower mean molecular weight, or both. Now, the mean molecular weight, partially you deal with it by taking the oxygen out, and that lowers your mean molecular weight. And then you add water. Because the atmosphere is very hot, the fraction of water is higher, and that lowers the mean molecular weight some more. You can't do it with CO2 very effectively, because carbon dioxide will increase your mean molecular weight, and it makes it harder to get a bigger scale height. So to show you what you need to do, and this is from Wu et al., and they use GCMs for this, to get a 19-hour day, you need a temperature of 50 centigrade. That's very hard to believe, but worth thinking about. Hot, really very hot. And in their figure, because this is one of their results, Wu et al. Argued at the surface, they took with this and they ran with it, and they made a history of the temperature. And ignore this thing, this green thing that is attributed to me, because we didn't do that. I don't know what they did, but and then they blamed us for it, but we didn't do that. This is what they did, and the blue thing. It's hot. It's 50 centigrade. And so it's one of the results that the boring billion were hot. We'll come back to that. So I've just I've done this myself with moist adiabat. which is a water dominated as you get the higher temperature. Water becomes a bigger and bigger constituent in the atmosphere. And I think 40 centigrade will probably do for a 19-hour day. I think the GCMs are probably actually getting a better shape, these shapes. So I shifted the Wu et al. Curve so that it actually has the right resonance period. And that shifts it to the left a bit. The sources of data are terrible. People count growth rings and stromatolites, which could be interpreted as days per year. They count rhythms and tidal deposits, which would be like tides per month. Maybe semi-diurnal per fortnight or things like that. Maybe months per year, you could also try to do. You can try to determine Milankovitch cycle periods. This is we're talking tens and hundreds of thousands of years now. This is called cyclostratigraphy. It's the newer approach, and it seems, I think, the most promising approach because there's potential to find other ways of constraining the length of time being spanned by a sediment. When you're talking about growth rings and rhythms, you don't really know the time at all. Your geologist is saying, I know what I'm looking at. And then another geologist will come along and say, I know what I'm looking at, and then they'll have a fight. So you don't really know what they're looking at. And you don't know how long it took for these deposits to accumulate. But when you're talking about hundreds of thousands or millions of years, there may be other ways of determining how long that period of time is. And that gives cyclostratigraphy a leg up. The Milankovitch cycles all change as the Earth rotates more quickly and the moon moves to different distances. And so the beating between the different cycles changes. And so that's what you'd be using as a means of determining the distance to the moon and the rate and the length of day. Okay, this is from Laskar. And he points out, they point out that the Wu et al. Retrieval depends very heavily on stromatolite data. So these are attempts to estimate the length of day from the rate of growth of stromatolites. Stromatolites are these bacterial constructs. They make these rocks they are known to respond to daylight for this. So like they could put down a new layer every day or maybe a new layer every year. Because they're rocks, they preserve well, and because they're made by simple bacteria, usually cyanobacteria that are phototrophic, they go way back in time. So most of the most interesting truly ancient evidence of life on Earth are stromatolites. So the heavy reliance on these data, but this is the official Farhat curve, I believe, which is the curve to be believed in this room that I'm talking to. And this is a new cyclostratigraphic datum that I didn't know about that seems to verify the purple curve, or at least support the purple curve. A similar sort of view, jaundiced view of the Mitchell work is, again, the Mitchell stuff depends heavily on the stromatolite data from Piniella et al., 1972. And Piniella himself said, don't put too much weight on this. This Grotzinger datum is under construction, so we don't know what it is yet, really. This is a cyclostratigraphic point from Myers et al., and that's quite an interesting one. But they do assume constant Earth-Moon angular momentum, so this is not correctly plotted. It hasn't been done quite right yet. So this is the Farhat preferred history, taking into account this is the Bartlett and Stevenson version of the constant day on their preferred history of lunar orbit, which is very traditional looking, kind of what you might expect. And of course, I get the blame for going back to 4 billion years, and I deserve the blame for that because I did draw a dashed line going back to 4 billion years. Their preferred history is only modestly impacted by atmospheric tides. So I'm going to finish off with a few minutes. Let's pretend that it did lock the length of day. Let's pretend that the Zahnle and Walker hypothesis is actually correct, and that these 19 to 20-hour days were locked for 1 billion years. How are we going to estimate the resonant amplitude? Well, the amplitude of the torque depends on solar heating of the atmosphere, not on the pressure, not in the total mass of the atmosphere, but on the solar heating of the atmosphere, how much energy is being absorbed, and on the dissipation that's associated with the resonance. While dissipation is known from Sakazaki and Hamilton, they worked it out from the width of the forced modes. So they retrieve these modes, and then they fit it to Lorentzians to get the dispersion associated with the free mode. We're interested in this one here. Actually, that one is particular, but they don't get a very clear picture of the mode that we're most interested in because it's still close to the force mode. The damping time is about 2.5 days, maybe 3, something in that range. And we're concerned with that. So the damping time corresponds to a Q of around 30. So this is the observed damping of the unforced normal mode. Is comparable for this particular mode to a Q of around 30. I would just, that's not as dissipative as 10 that the GCMs get, but it's not as undissipative as I would like to get a really nice big resonance. Solar heating. Ozone is the most important forcing today. Ozone absorbs about 2.5% of incident sunlight, so we still have some room to add atmospheric heating if we can put other absorbers in the atmosphere. You can get bigger amplitudes and therefore bigger torques if you have other absorbers. In a hot atmosphere, you'll have a lot of water vapor in the atmosphere at high altitude, and you can absorb that. And that can absorb sunlight at, say, a micron or places like that. And you can put methane in the atmosphere because as a modeler, we always do whenever we want to do something that's invisible and yet will have effects. We put methane in our atmospheres. And methane absorbs near visible light as well. As you can tell, if you ever look at pictures of Neptune, you'll see how blue it is because all the red's been absorbed by methane. Or you can have absorption by dust or by clouds. Water ice clouds can absorb IR from the sun, and dust can absorb sunlight. And these can also, on Mars, dust and clouds drive the thermal tides, not the atmospheric absorbers. So we did a little toy model of this. Nick Wogan actually did the little toy model. And he went for a surface temperature of 314 K. We couldn't go any higher for reasons which we could do models with higher surface temperatures and more methane, but they are impossible models biologically because biology cannot produce that much methane at that high temperature. So this is about the hottest we could go. And we made it hot by 100 ppm methane as a greenhouse gas. So this atmosphere is 100 ppm methane, and because surface temperature is 314 K, it has a lot of water vapor in it. And so the green curve is the atmospheric heating versus today, the black curve, and the ratio is the red curve. So a hot atmosphere is going to absorb maybe 3 times, 4 times, 5 times more energy than the modern atmosphere would absorb. And so the amplitude of the thermal tide will be a few times, 2 to 5 times higher than it is now in this hypothetical hot atmosphere. So the hypothetical hot atmosphere is absorbing more sunlight by a factor of a few, hence the tidal torque is bigger by a factor of a few. So as a toy model, I show you the consequences of that. Your basic model would have a 5 millibar amplitude at resonance. If dissipation is half of what is observed to be, Q of 60, you get a 10 millibar amplitude. If you take this 5 millibar guy and you give it 5 times the radiative forcing, you're up to a 25 millibar. So this is a 2.5 day damping period with 5 times the radiative forcing, and the amplitude would reach 25 millibars, which was going to cause a lot of weather. The balancing torques is harder to do. Even with this red curve, we're barely able to get a balance. Sustainable average lunar tidal dissipation is in this blue range, and it is possible to get a balance with this hot atmosphere, because there in the atmosphere you have a lot of water vapor and methane that allow you to have more radiative forcing. So it is possible to get, it's not impossible to get this 19-hour day, because you can have big enough tidal torques on the thermodynamic. The thermodynamic acceleration can be big enough under those circumstances. This is from Russ Dietrich and Colin Goldblatt. They actually have tried running a model, a GCM. Their GCM is resonant at about 22 hours and not 23 hours, as in the Wu et al. GCMs. And what they're showing on the right hand here is that today, you can see the tide. It's actually quite clear in their model. And what I'm plotting here is actually is called the horizontal divergence, and this is what kind of drives weather. But if you go near resonance, it's very well structured. It's very clear. And if you look at the consequences for rainfall, you see a nice semi-diurnal pattern in rainfall, particularly over the ocean. That's this blue guy here. Rains at sunrise and rains at sunset, and it's clear at noon. Forecast every day. But I note that this GCM is a different resonant period than the Wu et al. GCMs. One last point, one last thing to say is that if it's that hot, if you have a hot boring billion at 40 centigrade or 45 centigrade, animals can't live under it. Complex metazoa cannot live aerobically if they are too hot. Aerobic respiration does not work. They can't take the oxygen and cook it when the temperature gets above about 45 centigrade. Now, 45 centigrade is like, if that's the temperature every day here in the tropics. And these are killing curves. Apparently, biologists or zoologists with nothing better to do will take animals, various kinds of animals, and cook them and see when they die. Not something that I would do, but it's in the literature. So we'll wrap it up. Conclusions. The data do not really support a constant length of day in the Proterozoic. This point has been made clearly. They really don't. The long length of days depend almost entirely on stromatolite growth rings, and it's a very dicey source of information. The theory does not fully support constant length of day in the Proterozoic. The theory does not either. The Wu et al. Models, their tidal evolution models, are somewhat contrived. The resonance at less than 20 hours requires tropical sea surface temperatures above 40 centigrade. Torque balance requires low levels of oceanic tidal dissipation. Well, that's okay. That is credible. Torque balance requires higher amplitude atmospheric tides. It does. On the other hand, a very warm atmosphere will absorb more sunlight because we made it warm by adding methane. And because it's warm, it has a lot more water vapor in the atmosphere and in the stratosphere. And because it has more water vapor in the atmosphere, the tidal torques are bigger, significantly bigger. A hot Proterozoic has another interesting quality, which is that it frustrates biological evolution. So you get for free an explanation for why the boring billion is so boring. The complex aerobic metazoa cannot evolve because they cannot live. They require average temperatures smaller than 40 or 45 centigrade. So the boring billion would be explained simply by the high temperatures of the time of the locked day. So there's still reasons to pursue this topic for the present. We shouldn't just say, just because the stromatolites aren't favoring this. What we need is much better and much more cyclostratigraphic information and allow data to take its proper role in an inquiry which has been mostly dominated by theory. Thank you for your attention.
Thank you a lot, Kevin. You made really a lot of work. You put a lot of work in this presentation. I'm very glad to see all the small model you derived to try to show really the issue. So thank you for that. And I'm sure there will be a lot of reaction here. So please, if you want to ask question or make comment, raise a small hand.
Should I stop sharing the screen?
No, you can leave it because there may
Okay.
be questions that are related to some of your plots. Does anybody has? Yeah, Margaret. Yeah.
Hi. Thanks for the talk. Yeah, based on what you said at the end. So first of all, metazoa, from my understanding, didn't really evolve before 800 million years ago. So,
Yeah,
right?
I think
So I
so.
don't know. Yeah. Whether that would like be relevant for this issue, whether or not. Yeah.
Yeah. So we would argue that as a hypothesis that the reason complex metazoa do not evolve until 800 million years ago is because the temperature was too high.
Okay.
That's all.
Yeah. So you're saying that, is it possible that during this range in time where you had a certain where you're like close to this sort of frequency where you could have entered this resonance, could you have altered, like you're saying, is it possible that you, or not, we cannot exclude it now based on the lack of actual data, that you could have moved in and out of this thermal atmospheric tidal resonance locking multiple times?
Yes, I think you could, because it takes a while, it takes time for the Earth to adjust its rotation rate, because these are not extremely strong forces. They take a long time to act. And the climate moves much quicker. The climate can jump into an ice age on a dime, right? And then it can come out of the ice age on a dime. And that's how Bartlett and Stevenson got out of the resonance. They said, we'll get out of the resonance by first we'll cool the planet and move the resonance to a longer length of day. And then we'll make the planet hot. We'll come out of the snowball and make it hot. And now we're on the wrong side of resonance. And now the Earth just rotates away just decelerates away from the evidence from the resonance and never hits it again. So that was the concept, is that an abrupt warming will lead to escape from the resonance that's permanent. But if you have an abrupt cooling, you'll just encounter the resonance in the future. Is that clear?
Yeah.
The resonance is at a longer length of day, the colder it is.
Yeah. Third question, if I may. So your comments about Myers and Malinverno 2018, I didn't get that, what you were saying there. The 1.45 billion year old cycle point.
Yeah, I didn't know about this paper. The reason I'm into this right now is that I reviewed the Wu et al. Paper. And I was very interested in what they were doing, very interested. So that's where I learned about Myers et al., their 2018 paper, which was the first, to my knowledge, the first cyclostratigraphic stratigraphic analysis in the Precambrian, or at least
No. The first who calculated the precession frequency and Earth-Moon distance from cyclostratigraphic data. So they base it on, it's just a data, but the previous authors have produced the record and have suggested that this Zahnle formation was orbitally forced. Never mind. But but you were saying something about how they derive length of day, assuming conservation of angular momentum.
yes,
But
they
that's
did.
what that's what we all do, right?
Yes, but you shouldn't.
Yeah.
But you
You
shouldn't.
should,
Yeah, but
but how?
Because there are
No.
two things that affect it. The ordinary solar gravitational tides take angular momentum away from the Earth-Moon system, and the thermal tides, the solar thermal tides, put angular momentum into the Earth-Moon system, so that your angular momentum is not actually conserved.
yes,
But
It's a
so,
5 effect or something like that.
yes,
But it would affect your Milankovitch periods, and it would affect.
yes. Just a comment on that. In the primary, it is true that there need to be very distinct separation between what are the primary quantities that are really derived from the cyclostratigraph record, and this is the precession frequency. So, and then to go from the precession frequency to the length of the day, you need to go through a Earth-Moon evolution model. And it is true that the Earth-Moon, if you just take the Earth-Moon angular momentum, it is not conserved. But in the model, which is a small model that we run in the integration of the Earth-Moon system, there is also the sun. So this part is taken into account. So if you use this model to make the conversion, then it's taken into account. But of course, the atmospheric thermal tide that also change the angular momentum is not taken up to now into account, which would make a small difference. But it is true that many people who do a conversion, they don't take into account the sun. Some of them do. It's model dependent. But if you stick to the precession frequency, then it is not model dependent. I just wanted to make also a point is that Kevin, you mentioned the atmospheric model. This is really the work of the establishment of this atmospheric model is really the work of Pierre and Mohammad. Just to make things clear. That's have you finished, Margaret? Are there other?
Well, I'm so confused because you're also saying that cyclostratigraphy is more reliable method maybe to get robust data of the Earth-Moon system evolution from this Proterozoic interval. But if we're also saying at the same time that if this precession frequency is not going to how to go from that to length of day is not straightforward necessarily. Is it then actually a good proxy to test the atmospheric thermal tidal locking hypothesis?
I think it's newer and it has more potential because you have other ways of testing the length of time you're looking at, potentially.
Okay.
But Margaret, as I say, to really make the conversion to length of the day, you would, in the best of the world, you would need to have a complete model that includes also a model of atmospheric tides. You need to have the whole evolution of the angular momentum. So,
That's true.
but so it's more complex. But the precession frequency, this data is independent of the model. Any other reaction, comment, question? Pierre?
Yes, I have a question. Thank you very much, Kevin, for this very nice review of the different works. I had a question about something that you said at the end of the presentation, which is that Yes, in the past, actually, the sunlight, because there should have been 2 to 5 times more sunlight absorbed by the atmosphere, which would lead to an increased tidal response and an increased tidal torque. But I was wondering, because there is this effect, so this is a direct forcing, and there is another effect, which is the role that the thermal forcing plays in the efficiency of dissipative mechanisms. So shouldn't we expect that the efficiency of these dissipative mechanisms, radiative cooling, friction, or any other mechanism, shouldn't we expect that this efficiency increase if the planet gets warmer, which would decrease the resonant amplification, in your opinion?
Yeah, that's a good question. As you know,
Kevin, can I ask you to stop sharing the screen if you don't need, so we can.
Okay. Oh, hi. Yeah, that's a good question. First, I want to make the point to make clear that the higher forcing is specific to the hotter atmosphere, and that's where you get the higher solar forcing. The surface temperature is more of a diurnal forcing than it is a semi-diurnal forcing. The semi-diurnal forcing comes, the magnitude is big because it's black at night. It's dark all night long. The thermal radiation from the surface, though, is going to be much more diurnal. It continues to cool at night. So I'm not sure that you're going to get as big a semi-diurnal forcing out of that. The other thing is that when the atmosphere is much hotter, particularly the sea surface temperature, it's not going to change much between night and day. So I don't think that forcing is going to track the temperature as strongly as the direct forcing by water vapor and methane would track temperature, particularly water vapor, because water vapor is put in the atmosphere by temperature, and so that's a direct forcing. So that's my thinking anyway, is that the radiation from the surface will be relatively less important in a hot atmosphere than it would be now. It's also going to be more associated with continents, of course, because
I was on the point to ask you, Paul, what you're thinking about 50-degree temperature in the.
That's funny you should ask, because that's exactly why I have my hand raised. So my first question is, your 50-degree temperature is the average temperature.
I'm 40. I go for 40.
Oh, well, okay, but
50's woo. I'm 40.
What's the gradient look like pole to equator?
It's probably very small, because we're getting that high temperature through a greenhouse effect, and so the gradient between the tropics and the pole would be small. So the atmosphere would be more ideal.
And then the gradient from the surface of the ocean to the floor.
What's in the ocean? Under the water? I
From
have
the
no
top
clue.
to the floor.
I'd say the ocean's got to be hot all the way down, wouldn't you think? Because you're not getting a nice source of cold bottom water.
Right. So now, turns out that right now, at deep sea vents, we have metazoans living at the deep sea vents up around 45 degrees.
But they dip in and they dip out. They don't sit there.
No, there's actually a paper in 2013 on the thermal limit for metazoan life in vivo heat tolerance of the Pompeii worm.
Okay. That might have been in David's figure that I showed, actually, because David is the sort of guy.
But nonetheless, the global environment, even with 50 degrees, a very hot world, there's some heterogeneity, and right, and so
Mountaintops would be nicer.
Mountaintop, yeah, but it's also a bit. It's not good for evolving in water.
But there are other issues as well, is that if you don't have a lot of environments, then it's kind of hard to evolve. Because you kind of go from, there's the recruitment and so forth problems.
But still, like an argument against evolution has its substantial issues. But I think it's pretty clear that metazoans do have issues with no matter whether you have a Pompeii worm or not, up around as you're getting into the 40s and certainly around 50. And one would expect that you'd have more animals around at those higher temperatures if the limit were significantly higher.
And another factor here is that because the Proterozoic doesn't have as much oxygen in it, it's going to be harder for the Metazoans. Because the problem with high temperature is they can't use the oxygen.
Right.
So for them to survive a high temperature, you need to give them a lot more oxygen than you expect to have in the Proterozoic.
That's certainly true. That was a great talk. I really enjoyed it. Thank you.
Thank you.
June, pleased to see you.
Oh yeah, I have a so if I understand your presentation correctly, so if the temperature, the atmospheric temperature, ocean temperature during this boiling period is not as high as 40 degrees, for let's say if it's like just like normal, like a 10 or 20 degrees, this resonance doesn't work, or still?
No, the empirical arguments that the resonance occurred between 19 and 20-hour days precludes that a temperate temperature like 10 or 20 degrees. So the resonance hypothesis, according to papers by Mitchell and by Wu et al., requires a high temperature and a short length of day. That was not what we were expecting back in 1987. We were thinking it's all just all comfortable back there.
Okay. So I think so
it's driven by what is taken to be empirical evidence.
Okay.
That the temperature is high. So you could,
but
that if there is a locking in the day length at 19 and a half hours, it's basically a thermometer.
Oh, okay. So because there are people who try to like measure the like partial temperature by using triple oxygen isotopes, that kind of thing. So we can test that kind of possibility in the geochemical way as well, right?
Yeah, there might be. There are reasons to think that erosion is weathering and erosion are faster in the Proterozoic, but you already suspected that would be the case. There are no glaciations. So you know that on average it's warmer than it is now. I think you already knew that because you have no glaciations.
So can I just comment that, I mean, I don't know whether we can say that for sure. There was no glaciers at all, right?
I can say that because I'm ignorant.
The pure lack of data, right?
Yeah, it's a lack of data. But there's better data for the Proterozoic than there would be for the Archean, and there's plenty of glaciations in the late Archean. You got Pongola 2.94. You have the famous the Neoproterozoic snowball. You got a lot of glaciations in earlier, and you have them later, but you have a long period where you don't see any. That doesn't mean there weren't any, but why not have none? It's just it is an absence of evidence, but you do have evidence before and after of glaciations. So you know that it's possible to have evidence.
Jeremy Lecomte, who is co-authoring the Wu et al. Paper, was here during the talk, but he has left now. So
he's on the Wu paper.
Yes,
yeah. He ran some of the GCMs. I've always wanted a GCM person to tell me why they're not getting the right resonant frequency. Or fight back and say the analytic model is wrong and we're getting it right. But I haven't heard any GCM person give me an argument yet for why the GCM is getting the right frequency. So I was hoping that Lecomte would do that, and say, you're an idiot. But he didn't say that. He left.
He left, yeah. Frank, do you have any thought, any comment? Frank,
Yeah, I just following up on what Margaret's saying, I think maybe some of the best sedimentological evidence for ice that might be present, and not necessarily glaciers, but any form of water ice in the in large bodies of water, would be ice rafted debris, because with the absence of trees, the absence of any other mechanism, that would be the only way to bring large particles out in far out into the ocean or into very large lakes. And that's something that should be looked for. And I'm not sure it is looked for that much. I
Well,
know,
we don't have pelagic records, of course, right?
well,
Of
wouldn't
the-
it be pelagic records, because you're actually depending on shoreline freezing.
Yeah. So I think if you, I mean, looking for obliquity signals in cyclostratigraphic records could also be an indicator, right? Although obliquity not necessarily only means high latitude glacial-eustatic climate influence, but yeah.
Any other comment or?
Well, so I'm so curious. I didn't follow everything, but how Kevin's comment about the GCMs relates to Muhammad's 2024 paper. Like, are you now sort of, yeah,
Maybe
because
Mohammed can comment on that.
Yeah, on what specifically?
The way you see because Kevin spoke about the change in the atmosphere mostly, and the composition of the atmosphere, and how what is needed to get a higher torque, to higher torque at the resonance.
So what we have is basically, what we're sure of now is that both GCMs in Wu et al. And in the Dietrich Goldblatt paper predict an amplification which is similar to what we have in our analytical model, which is not sufficient for the locking hypothesis, because we had an analytical model, and then there was the other papers that Kevin mentioned, Bartlett and Stevenson and so on, and they predicted much higher amplification. And so we were not sure about the amplification we're getting. And that has to do with the dissipation that Kevin was talking about. But what we know now from the Wu et al. Paper is that what they got with the GCM is not as much as what they needed for the locking, which is consistent with our model. And the other paper, which is coming soon, I hope, in Nature Geoscience, the Dietrich et al. Paper, they also have a similar amplification factor, which is also not sufficient for the locking. But Kevin, it seems I underestimated the importance of the Sakazaki paper because I haven't looked to it thoroughly as you did, and because we were looking for specific observational constraints on the dissipation timescale, and we did not find any. Yeah, and we have. Yeah, so now we know it. Pierre can also is a witness to that, because we did not have any observational constraint, and we went to derive some ourselves. But it seems that the constraints they provide now are also consistent with the estimates we had in our paper. But I want to go back to Pierre's comment, Kevin, because I think you misunderstood his point, although you brought another important point, but it was not the question he said, which is that indeed a warmer planet would absorb more energy, but a warmer planet will also dissipate more energy. So you would have more absorption, more tidal response on one end, but you would have more cooling, at least for radiated cooling. You would have more efficient cooling, and you would have more attenuation of the tidal response. So I think you emphasized on the first part, but you did not comment on the second part. And I think that's Pierre's comment, not the idea of synchronous and asynchronous heating.
No, I didn't catch the second question, but
Yeah.
you're saying that yes, it's hotter, so therefore the radiative cooling would also be higher.
We know that by equation, because we know the proportionality between the cooling time scale and temperature.
But you don't know that's the source of the actual source of dissipation.
True, that's true. Yes, that's
but you
true.
know there is dissipation, and we
Yeah,
know
yeah.
how it is, but we don't know if it's radiative cooling that does it.
Maybe more.
Yeah.
Radiative cooling is a nice choice because you can incorporate it in the linear model and you can solve it. So that's why.
What is it? Sorry, come again.
Oh, you can solve it because it goes in the linear model and boom.
Yeah,
That's how you do it.
yeah,
That's the right thing to do.
yeah,
I did that in '87 too. We actually did radiative cooling.
exactly. Yeah.
If you look at our figure with the low Q, it also is asymmetric like yours. The torque.
Yeah.
Maybe it should be reminded, Mohammed, that in Wu et al. Paper, the resonance locking was not obtained by the GCM.
Yeah.
Might be confused for some people here.
Yeah, this is a very important point. Yes, indeed.
It's two separate things. They had to get the resonance, the locking, they had to put some artificial factor amplifying the effect.
Yeah.
And this was empirical in order to fit the data.
Mm-hmm.
And it was not the outcome of the GCM.
Yeah.
Any other comment by atmospheric? We have quite a very diverse audience here because we had specialists of the atmosphere, paleontologists, geologists, celestial mechanics, geophysicists.
Indeed, yeah.
Which is nice on this problem. This is really what is needed. And
So we need biologists because Kevin made a very nice perspective on biology. I was not aware of that. Thanks for that.
yes, that's. But that was why Paul was commenting, because he knows about the evolution. Paul is a paleontologist, so or geologist, paleontologist, is a lot of. Any other comment? Yes, Frank?
Yes, I was surprised that there is no constraint on the temperature, for instance, of the ocean during this long 1 billion year period from isotopes or whatever, oxygen, or there's nothing we can use to constrain the temperature?
There are contentious constraints.
Yeah.
You mean like the one that were made for earlier periods with silicon and oxygen? They are the same kind of
isotopes, which nobody believes simply because
Yes, I know.
I think it did that. I don't think that's right. That's the usual argument against it.
Hard to do for the Phanerozoic.
Yeah.
Yeah. I was not naively assuming that there might be some more solid constraints for more recent period of time.
No, it's very contentious, yeah. But it's the same kind of constraints. You have oxygen on one end, phosphates, carbon cycle models also, and the analysis of glacial deposits. But yeah, it's very contentious, yeah.
I know from a study who do clumped isotopes of near Proterozoic carbonates, that seems to work pretty well. So I don't think it's like hopeless. Clumped isotopes. Yeah, Ilya knows more about it. So, but it's yeah, on dolomites. Apparently, they're quite stable. I saw a talk about that. That's online a couple of weeks ago. So
I would defer questions for this to David Catling because he actually has been thinking about.
Yeah.
He knows more. He knows more than I do about everything, but he knows about this.
Okay, so that was really a nice session. I really
I'm just saying goodbye. I was just saying goodbye and thanking you for your attention. You were a very nice audience. I should bring you home to me.
Yes.
Love to bring you home.
Yeah, no, that was really nice, and you put some new ID that were they are really motivating. We can think about that, and we will meet again in a few time. I have to think about the next session. I have one topic that is in view, which is the oceanic tide. And we will have a talk on oceanic tide quite soon. Okay, so thank you for everybody, and let us meet at the next AstroGeo meeting.